My name is Wayne Ottinger. I started my aerospace career in June 1955, an opportune time just before the space program really took off. This lecture will focus on the early spaceflight-related history as the Cold War heated up after World War II in the mid-1950s, greatly stimulated by Russia's launch of the first satellite, Sputnik, on 10/4/1957. U.S. aviation progress after World War II brought in the jet age, transforming both military and civilian applications while providing a significant growth in employment and economic benefits. I intend to include untold stories of how challenges were met during the 6 decades of aerospace progress. This clip is from the Discovery Channel, from the Great Books series, The Right Stuff. This reported interview with Nikita Khrushchev's son, Sergei, about the Cold War is revealing. It certainly is an example of the driving force of fear, particularly that generated by the ignorance of true facts. My cousin, Dale Miner, was the executive producer for the Great Book series.
But Russia was still winning the race. Kennedy had a novel solution that Wolf did not include in his book. In Vienna, 6 weeks after Shepard's flight, Kennedy proposed ending the competition by combining the two space programs. Nikita Khrushchev turned him down. Khrushchev used to walk in the evenings with his son Sergei. Sergei asked his father why he wouldn't cooperate with the Americans. The Russian leader replied,
"It will mean opening up a rocket program to them. We have only 200 missiles, but they think we have many more."
Sergei asked,
"So, when they say we have something to hide?"
Nikita Khrushchev laughed.
"It is just the opposite. We have nothing to hide. We have nothing, and we must hide it."
When we're talking about disparity between Soviet Union and the United States, it was huge. Really, Americans in 1955, when my father first met with President Eisenhower in Geneva, had everything and we had nothing.
Unknown to Western analysts, many of the missiles in the May Day parades, symbols of Russian might, were wooden models. Russia only had 5 that could make it to America. The whole space race was an enormous smokescreen to conceal Russian weakness. And it was working. The space race continued unabated.
This clip is from their disc, One of When We Left Earth. It starts with the X-15, which flew first on June 8, 1959, and ends with Project Mercury, which flew Ham, the chimp, on January 31st, 1961, and Alan Shepard on May 5th, 1961.
In the high desert of California, NASA tests an experimental rocket plane, the X-15. They want to put a man into space, and they're in a hurry.
Rockets were powering aircraft to higher and higher speeds. The X-15 had enough energy to zoom to altitudes above the atmosphere.
The X-15 flies so high, pilots experience weightlessness and look out into the darkness of space. But even at 600,000 horsepower, it would need to fly 4 times its top speed to put a man into orbit. The Soviet Union holds an early lead in the space race, launching the first unmanned satellite to orbit the Earth.
On October 4th, 1957, when Sputnik went into orbit, People were so upset. They said, these people can't build a refrigerator. How can they get into orbit? How did this happen?
To beat the Soviets, NASA must launch a man into Earth orbit. Only rockets can go fast enough, more than 17,000 miles per hour. They call the program Project Mercury, and rally a team of determined young scientists and engineers to figure out how to fly a military missile with a man on top.
Most of us came in from aircraft like this. We knew nothing about rocketry, we knew nothing about spacecraft, we knew nothing about orbits.
Gene Kranz joins the flight directors team in NASA's earliest days.
So it was a question of learning to drink from a fire hose. We had to learn all about trajectories. I'd never heard the term retrofire, coming on down from orbit, getting the spacecraft back home.
A few weeks after I arrived at the NASA Flight Research Center as the X-15 propulsion engineer, Powers was shot down, as well as a Russian fighter pilot who died trying to intercept the U-2. A U-2 stationed at Edwards in secret was brought to the NASA hangar by the CIA overnight on May 1st, and the tail painted with the NASA logo. On May 2nd, our chief test pilot, Joe Walker, had to taxi the U-2 for the press conference that morning, having never seen the airplane before. At the May 17, 1960 Peace Summit in Paris, Khrushchev pounded the table with his shoe, confronting Ike with the physical evidence with the spy cameras recovered, rightfully challenging the lie Ike was telling. It was a NASA aircraft on a peaceful mission, unquote. I met Powers several years later after his release from Russian prison on February 10, 1962, in the prisoner swap for Russian spy Rudolf Abel. Powers died in a news helicopter he was piloting on August 1, 1977, in Los Angeles. On February 1, 1961, I was in an X-15 post-flight meeting at Edwards, and our former director at the NASA Flight Research Center, Walt Williams, who was the new director of operations for Project Mercury, had just returned from the Cape and told us the story about Ham, the chimp's flight on the Redstone Mercury on January 31st. Walt told us they thought they had trained Ham well, exposing him to the expected flight hazards, but indeed they forgot one. The capsule escape rocket, designed to be used in a launch emergency, was ejected after the normal launch, and they forgot to include that rocket blast of it leaving the capsule in Ham's training. Ham had learned on his own to use a shortcut he developed to get his banana chips, with significantly less keystrokes than he was trained to use, a normal behavior for his routines. The film taken through and during the launch revealed he had abandoned his shortcut when the escape rocket leaving the capsule had scared him. Ham immediately reverted back to his keystrokes as trained. It is quite revealing that none of this story was ever told in the official NASA reporting documenting the detailed training and performance of Ham on the mission. Human pride blocking out significant report on animal intelligence and behavior.
1961. The rocket and capsule are finally ready to fly. But none of the astronauts are happy about NASA's choice. A specially trained chimpanzee named Ham will fly the next Mercury mission.
There was a group of professional naysayers in Washington who insisted that we do some more work to prove a 5-minute flight wouldn't be fatal to man.
NASA's medical team sends Ham as a final test that man can function in zero-G. The astronauts fear they're losing precious time.
None of them liked it. Alan was fighting to get rid of the chimpanzee. He didn't want the chimpanzee to take up a rocket to take up a seat.
January 31, 1961. Ham blasts off on a suborbital mission into space.
2, 1, 0. Liftoff.
While weightless, Ham's put through a series of tests and performs well. Physically, he's unaffected by zero-G. Ham splashes down off target. He's fatigued, dehydrated, but generally in good shape. His mission proves man can function in space. But doubts remain about the reliability of the rockets. And they still don't know who will fly first.
Edwards Air Force Base was on combat alert with the highest security during these few weeks. Getting on and off the base was quite an experience. I was supposed to have moved to Niagara Falls, New York, or Buffalo with my family with the 4 small sons in August that year, but was on standby to late December till NASA funding came through to get the LLRV design build contract underway at Bell Aerosystems. Our competition for lunar landing training included the MIT position that no free flight training was needed, as well as this lunar landing research facility at the NASA Langley Research Center in Virginia. The astronauts and our 3 research pilots all flew this heavy cable suspended vehicle, which provided some value, but was plagued with difficulties competing with our free flight simulation qualities. I recently encountered engineering personnel from Langley that had no idea what this facility that is still there was used for. For this Bell photo, I was 30 years old, had been assigned as the NASA plant representative at the Bell Aerosystems Niagara Falls, New York plant for the LLRV design, manufacturing, and build for 14 months. Under budget constraints, much of the final assembly and testing was done at Edwards, assisted by about 20 Bell engineers and technicians that came to NASA FRC at Edwards for about 6 months. I was flanked by 2 Bell VPs. On my right was General Walter Dornberger, the former Nazi general in charge of the missile work at Pinnenubi, Germany during World War II, and Werner von Braun's boss. I'll take this moment to tell a few stories that come to mind. During the contract-related private telephone conferences with the folks at NASA FRC at home, I would use Dornberger's office, as he was just working part-time then. On his office wall was a large, beautiful oil painting donated to him by Boeing of the Dinosaur or Space Skip Glider project he conceived in the 1950s, with a brass engraved panel on the bottom of the painting. It stated essentially, quote, dinosaur born 19 so-and-so, probably in the early 1950s, died 1963, Mac the Knife, who was the Secretary of Defense, Robert McNamara. Another story is Ken Levin, the Bell LLRV technical director, threw an LLRV party at his home on Sunday, February 9th, 1964. The black and white TV was on during the party to watch the Ed Sullivan Show introduce the Beatles. The slides taken that night of my wife playing the guitar and me on the bongo board are in my memoir I have just written. Another story, my parents in the summer of 1963, Clyde and Pauline, with my Uncle Glenn and his spouse Ethel and Aunt Marie and her spouse Carl all came to visit. Bell was kind enough to take them all on helicopter rides over Niagara Falls, their highlight of their driving trip across the U.S. Joe Cannon was a famous test pilot at Bell. He was a local hero in the 1950s for attempting to rescue a stranded woman hanging desperately onto a log stuck in the Niagara River above the falls. His first attempt failed as his landing skid on the helicopter caught the water, tipping him over into the river, and now there are two rescues, which finally did have a happy ending. On June 19, 1964, well before the first LLRV flight, President Lyndon Johnson visited Edwards during the 1964 campaign with Goldwater. He was asked to mount the LLRV on the flight line along with the Air Force airplanes in a position to demonstrate the gimbal jet pointing to the local vertical. And the LLRV pitched and rolled about the gimbals. E.E. Beeler, Deputy Director of NASA FRC, instructed me, as the LLRV project engineer, to add a chemical to the hydrogen peroxide rocket system and have President Johnson operate the cockpit controls so that smoke would be expelled from the attitude and lift rockets. Refused, as Bell would void the warranty on the rockets, but convinced D that red light bulbs taped to the nozzles would give a satisfactory visual effect. The test cart was configured to make that work. However, the Secret Service would not allow the president to sit in the ejection seat in spite of its safety locks. Our director, Paul Bickle, and Chief Test Pilot Joe Walker had to stand with President Johnson as the Secret Service would not let him sit in the disarmed ejection seat. The 1964 election campaign was in high gear with Republican Barry Goldwater bumper stickers distributed with AuH2O, the chemical symbol for gold and water. Our machine shop made me a red warning light lens with that symbol replacing the H2O2 warning light for the hydrogen peroxide fuel. The day before the visit, I showed Paul Bickle, our center director, the special light flashing in the cockpit panel, but had to explain the joke to him. Paul laughed and left. However, the next morning, Dee called me and demanded I bring the special lens to his office. I had to tell him Joe Walker, our chief pilot, who was to accompany the president in the cockpit, had already left with the lens to switch it just before the visit. Turned out Joe never used it, saving my job. The LLRV and LLTV and the Apollo lunar module are matched in the extreme pitch and roll attitudes required to maneuver, contrasted to the helicopter flying on the Earth. All 6 Apollo landings were made in confidence, as the pilots knew how to fly close to the surface with large vehicle attitudes and fast depleting fuel quantities. In other words, envision a pilot with minimum fuel reserves having to make rapid horizontal maneuvers close to the lunar surface using 28 degrees of pitch angle instead of 5 degrees here on the Earth, or anxiously awaiting a much lower response of the landing craft to translate over a boulder or crater. Perhaps one of our most important challenges to provide invaluable design data to Grumman for the lunar module design was to establish how low the control authority of the attitude rocket control system could give adequate pilot control for simulated lunar landings. This in turn meant managing the dry and wet center of gravity for all flight conditions to very tight tolerances. The propellant feed system for the rocket fuel supplying the 16 90-pound attitude rockets, the 2 500-pound normal lift rockets used for lunar sim mode, and the 6 additional 500-pound emergency lift rockets had to be installed symmetrically on the vehicle and plumbed to provide balanced propellant feed from the 2 peroxide tanks mounted on the pitch axis of the vehicle. The same challenge, but easier, applied to the jet engine fuel tanks on the roll axis. This picture shows the 4 500-pound lift rockets on the left side of the vehicle next to the 30-gallon peroxide tank on the pitch axis. To the right of the rockets is the jet engine, front fan engine inlet mount. Each of the 4 attitude rocket clusters used 4 ground-adjustable 18 to 90-pound thrusters, 2 for pitch and roll, which were primary and test, and 2 for yaw, which were primary and test. The weight and balance fixture was used to determine the engine and the vehicle center of gravity, or CG. 3 scales, a clinometer, and a complex set of procedures were used to the following accuracy requirements driven by stability and control parameters for the flight research program. This included defining the lowest values of control authority for lunar landings to assist Grumman in the lunar module or LEM design. The exploration of the lower limits of control presented a real challenge to use the lowest control authority for the LEM landing stage, which was much heavier than the ascent stage that used the same attitude control rocket system. An over-controlled ascent would have resulted if the landing system control authority was too great. These research flights helped drive the LEM flight control system design to unexpectedly lower values of control authority. This meant real schedule challenges for the LLRV. This control authority testing required flight conditions with little or no wind. 1, the instrumentation had to be capable of determining the vehicle/engine center of gravity with 1/10 of an inch. 2, the takeoff CG had to be controlled to a 1/4 inch sphere. Some relief for the vertical tolerance was made. And 3, the in-flight fuel management CG had to be controlled to a 1/2 inch sphere. This evolved to require roll trim control in the rocket fuel or hydrogen peroxide system for dynamic balance during flight. The LLRV weight and balance fixture was adapted to also serve as an attitude rocket system hot firing closed loop checkout for the pitch and roll axes. Bungees were provided on each leg as soft stops. There was still an adequate range of motion for initial system checkout and pilot familiarization prior to their first flights. This setup was used throughout the entire LLRV and LLTV programs for pilot familiarization, contrasted to the single-axis test fixture on the next slide, which was only used once prior to the LLRV's first flight. I flew the initial CG fixture test with others to follow. The early jet and rocket systems testing was meticulously performed with detailed checklists, technicians with full protective suits, a problem in the summer heat, and unexpected delays for system and communication problems. Joe Walker, our chief pilot, was determined to be in the cockpit for much of this testing. My challenge was to mitigate his impatience as much as possible, protecting the crew from pressures from Joe's complaints impacting safety. All parties concerned learned and made it work, with very few incidents of note. MSC operations in Houston for the LLTV required all 3 LLTVs and astronauts being trained in LLTVs to operate on this fixture. The rainy environment in Houston motivated us to build a shed to protect the CG fixture testing from rain to improve our scheduling. The first time the shed was used in Houston, the Bell rocket engineer's name was Tom Stafford, and that night the condensate of the hydrogen peroxide steam collected under the shed roof dropped below, setting small fires, the death of the shed's use. The next morning, rumors were circulating at NASA MSC that Tom Stafford, the astronaut, had flown the LLRV through the shed, and that started the fires. Rolled eyeballs with that one. VTOL tether testing had historically a bad history as we were preparing for the first LLRV flight. This was the first fly-by-wire flight control system with redundant analog circuits with no mechanical or hydraulic backup systems. The previous slides showed the CG fixture providing adequate hot firing closed-loop checkout of the pitch and roll attitude control systems. This left the requirement to have closed-loop or hot, checkout of the jet engine running, and its gimbal hydraulic system used for lunar simulation mode with the rocket attitude control system operating for both the pitch and roll axes. The yaw axis was partially tested initially on the ramp with landing gear casters, which were later replaced with footpads to provide more stable takeoffs. This LLRV single-axis test fixture was to provide the hot firing or closed loop operation of the roll axis as shown here. Then by picking up the vehicle with a crane and rotating it, we checked out the pitch axis with identical system checkout procedures. This provided all the system's closed loop testing required for the first flight without the risk of traditional VTOL tether tests. Custom bearings were made for the gimbals here. We had just moved our operations from the main NASA facilities at the Edwards north end of the main base to the south base to stay out of the main traffic pattern for the runways and lakebed. My flight controller communications for the first few flights with the pilot was from a NASA vehicle, known now as an SUV, then known as a carryall. We quickly acquired a modified motorhome stuffed with instrumentation and radio and telemetering gear. Soon after, Joe, as chief test pilot for the center, assigned himself to be the project pilot on the new LLRV project. Lieutenant Colonel Jack Kluver, on loan to FRC from the U.S. Army Aviation Test Facility at Edwards Air Force Base, took Joe up for a helicopter ride over the lake bed. He had Joe try to hover their helicopter, a first-time attempt for Joe to control any helicopter, even though Joe had already made the record altitude X-15 flight to 354,200 feet. This was on a Friday. On the following Monday, Jack asked Joe Vinsel, our director of flight operations and Joe's boss, where Joe was today. Vinsel's answer, Walker's in Pensacola starting the helicopter training program. Joe didn't waste any time once convinced of a challenge. It was a natural that when he left the LLRV project so he could fly the XB-70 Mach 3 experimental bomber coming to FRC, Jack Kluver joined Don Malik to complete the LLRV flight research program at FRC before they were modified for astronaut training in Houston. On the left is the photo Life magazine used for their special issue on Apollo simulators, 2.5 months before our first flight. They came to take the photo on the day of our design engineering inspection, where all NASA centers sent representatives to give us recommendations for a do list before we made our first flight. The picture on the right is Neil's last training mission, 1 month before Apollo 11 launch. It was mid-afternoon when we accommodated the Life magazine photographer. He wanted us to tow the LLRV onto Rogers Dry Lake bed, adjacent to the NASA FRC, broom out the tire tracks on the lake bed from the LLRV transporter, and position the LLRV with nothing in the background. Both Neil Armstrong, who was accepted into the second group of astronauts in September '62, and Joe Walker, the chief pilot for the NASA FRC Center, and Neil's former boss, were sitting in the cockpit for 2 sets of photographs. As you can see, the strobe light used with the afternoon sun in the background gave testimony to the ingenuity and skill of the Life photographer Ralph Morse. But it was still well before our first flight. Paul Bickle, our center director, agreed Life could get the pictures to include the LLRV in their special edition featuring simulators for the space program. In the summer of 1966, 2 years later, Morse and I were having breakfast in the hotel across from the NASA Manned Spacecraft Center, MSC, now the Johnson Spacecraft Center, south of Houston. I asked him for a copy of the picture he took. Later, when it arrived, I was pleasantly surprised that the large print was the shot taken with the late Joe Walker, easily recognizable in the cockpit. Joe died in the mid-air collision of June 8, 1966, and I thank Ralph Morse for providing me with this valuable photograph just a month or two after Joe's fatal accident. My colleague at FRC, Dick Day, had just joined the NASA MSC Flight Crew Support Division, found Neil's application for the second round of astronauts was rejected, as it was 1 week late. Dick moved it into the acceptance slot, surely unaware of the potential historic implications. Dean Grimm on the left, next to Neil. After Neil's last LLTV flight, Dean managed the LLRV and LLTV programs for the NASA Manned Spacecraft Center. The Ellington Field-Based Radar was determined to be emitting large electromagnetic radiation, or EMI, interfering with the flight controls on the LLTV just 1 week prior to Neil Armstrong's scheduled first LLTV training, delayed by the loss of the LLRV number 1 ejection on May 6, 1968, and the LLTV number 1 ejection on December 8, 1968. The accident investigations and corrective action required to proceed with the pre-flight training had delayed the start of the first LLTV training until just 1 month before Apollo 11's scheduled launch for July 7, 1969. Neil's success in flying the LLTV for a much reduced training syllabus was a mandatory requirement before launch, and the Bell team of engineers at Ellington Field scrambled near the end of that week to come up with a fix for the newly discovered EMI interference with LLTV flight control electronics. It came through in less than 48 hours and threaded the 3-day schedule. Neil had to leave the Cape in Florida, fly the LLTV training flights to where he was satisfied he was ready for launch. Turned out to be 6 LLTV flights before returning to the Cape for final launch preparations. NASA's top brass was both surprised and delighted. The Ellington LLTV team pulled it out of the hat here together with Neil's piloting skills, enhanced with his previous 21 LLRV flights and participation in the early LLRV design and development activities. Soon after the first LLRV flight, we received the modified Ford Condor motorhome, which we stuffed with telemetering and communication equipment. We had several engineers assisting me as the flight controller, communicating with the pilot. Behind me were several strip chart recorders displaying the Attitude rocket's firing pattern, and we could determine duty cycles to advise the pilot of excessive loss of control authority. Other lift rocket and jet fuel instrumentation allowed more accurate assessments of warning lights instead of depending on tank sensors and sloshing. We always had a good handle on fuel reserves, not so in Houston in spite of their watching our operations for several months at Edwards. The bid in the contract for the LLRV and TV transporter went to an Oregon trailer manufacturing company for $800, a real deal. The cockpit side windows were, as delivered from Bell, were soon replaced with a new design, eventually dictated by improved simulation of the LEM cockpit. The 90% hydrogen peroxide used at that time required continuous monitoring of the servicing tank temperature, and a water cooling system was used to prevent slow decomposition of the fuel to dangerous levels. Crews wore full protective suits to prevent burn injuries and fires. Lots of water was used to flush and dilute any leakages or spills. At the end of operations, flushing of the rocket system catalyst beds with nitrogen gas were used, which provided spectacular steam clouds from the hot rockets. The late Bill Willie Wilson was the second crew chief, supplementing the first crew chief, the late Ray White. Ray's expertise was invaluable to get the LLRV assembled and systems checked out using extensive checklists and maintaining superb configuration control for the flight research program. Bill Wilson, initially serving as a jet engine rocket system mechanic, earned his stripes over time and earned promotion as a crew chief to supervise pre-flight fueling and flight operations. One lesson he had to learn, though, was to always use the checklist. On one occasion, he had purged the primary attitude rocket control system, but had forgotten to select the backup attitude rocket system before taking the LLRV into the hangar for the night shift. The instrumentation technicians that night started exercising both rocket systems, checking instrumentation, and the small hangar, large enough for 2 LLRVs and test equipment, erupted into a number of small fires set by 90% hydrogen peroxide spitting out of 8 attitude rockets distributed at all 4 corners of the vehicle. Paint burned off test carts, wooden crates burned holding 5-gallon water bottles, belts burned on personnel in the way, a scene of chaos indeed. I had to choose how to reprimand Willie, which was a stern reprimand that he always used checklists and learned from the mistake. It worked. I hired him as the maintenance chief for the Houston operations on the LLTV when I moved over to Bell as the LLTV technical director. The pilot's instrument panel was initially located at the center of the cockpit, forward of the envelope needed for the operation of the ejection seat to clear the pilot's legs. Later it was moved to the right side as the cockpit and enclosure were redesigned to better simulate the limb. All the instruments were custom made by our NASA FRC machine shop to be proportionally larger as the pilot's eye distance was larger than the limb pilot's due to the use of the mandatory ejection seat, not appropriate for the limb. Following the 45th anniversary of the lunar landing by Apollo 11, which was held on July 20th, 2014, NASA released this short video, which included a portion of Neil's 33-minute speech at the 51st Symposium of the Society of Experimental Test Pilots, Anaheim, California, September 29th, 2007. I assisted Neil in preparing for that speech, furnishing both technical information and photos.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space.
Soon after President Kennedy's call to go to the moon in 1961, a number of researchers began to think about the various aspects of a lunar flight. NASA's Flight Research Center at Edwards proposed a free flight lunar landing simulator program. The research test vehicle was intended to investigate the inherent problems of lunar descents where there is no drag and weight is only 1/6 of Earth. The proposed technique for simulating the lunar gravity installed a jet engine underneath or within the machine on gimbals, so the thrust was always vertically upward. The engine thrust would then be adjusted so that the craft's net weight, that is its gross weight minus the engine thrust, would equal its lunar equivalent. The force required to lift the net weight would be provided by throttleable rockets. The first flight of the LLRV in October of '64 was flown by Joe Walker. First liftoff was what you might call tentative. The second was considerably smoother. During the following year, Joe Walker and Don Malik flew about 150 development flights, expanding the flight envelope and investigating the adequacy of the design and the systems. An advanced version of the LLRV, the Lunar Landing Training Vehicle, or LLTV, proved to be an excellent simulator and was highly regarded by the Apollo lunar module crews as necessary to lunar landing preparation. Typically, the pilot took off with the gimbals locked, flew out to the inner marker, which in this case was about 400 to 500 feet altitude, about a quarter of a mile from the intended touchdown spot. Arriving at the IP, he began a descent toward the target, switched into the lunar simulation mode, energized the lift rockets, and practiced the lunar landing. I was most fortunate to be involved throughout the entire lunar flying development. I had the pleasure of flying every one of the machines. the LLRF, the ground-based simulators, the LLRV, the LLTV, the lunar module, and even the Weber ejection seat, the last not by choice. NASA management was forever worried about the reliability and safety of these machines and continually wanted to shut them down. But the pilots insisted they were vital to lunar landing preparation, and they prevailed.
Drift into the right a little. Good. Safe. Contact light. Okay, engine stop. We copy it down, Eagle. Tranquility Base here. The Eagle has landed.
Thank you, Neil, Buzz, and Mike. We're standing on your shoulders, building on your historic achievements. That drive to reach higher is alive and well in today's astronauts, who will travel aboard Orion on our very challenging path to Mars.
This is a short clip from a NASA video titled 300 Feet to the Moon, which included rare footage, including a soundtrack of the 16 90-pound thrust attitude rockets and the two 500-pound lift rockets used to simulate lunar maneuvering and the jet engine to cancel the 5/6 excess Earth gravity to make a realistic Earthbound free flight simulation for lunar landings.
Before an astronaut ever actually flies a LLTV, he has trained in a helicopter for at least 100 hours. He has trained in an LLTV simulator, completing a detailed program, or syllabus, as the pilots call it. He has trained in a vehicle tethered to a large overhead frame. He has handled the LLTV mounted in a fixture where the vehicle will respond to certain flight commands. And he has powered up the LLTV engines with the vehicle itself tied down to become accustomed to the operation of the engines. Only after the considerable training, plus many briefings, is he ready to fly the LLTV. And in the total picture, this is but a small part of the training necessary to learn to fly the lunar module itself.
The LLTV training operation at Ellington Field, just north of the NASA Houston complex, which is 25 miles south of downtown, was integrated with the NASA manned spacecraft aircraft operations, including a large number of T-38 jets, helicopters, and transport aircraft. The base was and is hosted by Texas Air National Guard's 147th Reconnaissance Wing.
Over takeoff. -1 on the H-stop. Hands off for your balance. 15 feet per second. He has the plate. I'm hovering at 99%. Local vertical. Local vertical. Altitudes approaching 100. That's about it. There's about a 9-degree cross. Climbing. Balance is good. Thank you. And the wind is reading 25. There's the landing simulation. Okay. This altitude is 300. 2 minutes to JP4, 50%. Thank you. Approaching 40% go. Okay. When our sim switch is on, camera's on. Okay. Approaching. Keep drop off now then. Sorry. Okay, now I'm showing a crosswind here of some magnitude. It should be coming forward now. Okay. Showing 32%. Everything looks good. Outer throttle looks good. Gaugeable lock is off. Airspeed is all the way off. Not bad. Airspeed drops below 30. Descent rate's 10. Altitude's 200. Parking board. Okay. Airspeed's dropping back 50. Altitude's approaching 100. 1 minute to 50%. Q. Descent rate's 4. Altitude's 100. Descent rate's 4. Airspeed's 5. Touchdown.
The Gemini 4 mission's first attempt at rendezvous by Jim McDivitt and Ed White on June 3, 1965, failed due to a lack of understanding by the mission planners of the orbital mechanics required to accomplish success. This was a critical requirement for the Apollo program, for this was mandatory to be safely accomplished with a chosen overall scheme to get to the moon. This video clip is taken from a NASA documentary. First, there is a remarkable story to tell how it was overcome and success achieved on December 15, 1965, just 6.5 months later. This video clip of the Gemini 6A crew, Wally Schirra and Tom Stafford targeting Gemini 7 in orbit with Frank Borman and Jim Lovell aboard during their 14-day mission. Rendezvous was on December 15, 1965. Dean Grimm managed the LLRV and LLTV programs for the NASA Manned Spacecraft Center, now the Johnson Spacecraft Center, and was gone from our program as our customer while he took the primary responsibility to develop new orbital mechanics to correct the failure of the first rendezvous attempt by the Gemini 4 on June 3rd. He told me his story soon before his death in April 2014. NASA MSC at Houston had just installed a $40 million mission simulator, and Dean requested they run the rendezvous simulation backwards so he could identify maneuver errors and develop corrective actions. MSC computer experts said no, cannot be done. So Dean contacted his classmate from the University of Kansas, or KU, who was running the McDonnell Douglas Gemini mission simulator at their St. Louis facility. He got a positive response, went through NASA headquarters to get permission to take the 2 astronauts assigned to the next mission to attempt the rendezvous on Gemini 6A, that was Wally Schirra and Tom Stafford, to St. Louis and use that simulator to solve the problem. Dean got the go-ahead. About 5 months later, they presented their solution at NASA headquarters. NASA's red team, Boeing, recommended their solution would not work and that they be given the task to develop new procedures. He announced he would resign from NASA should they accept Boeing's recommendation. Schirra also said he would resign from the mission unless NASA accepted their solution. NASA accepted their solution from the Gemini simulator in St. Louis, and a month later, the Gemini 6A mission succeeded. Subsequently, Dean returned to our LLRV, LLTV program. Elliot C. featured in the video clip as the ground controller communicator, later killed in the T-38 accident on 2/28/66. The GE test pilot, and I remember from our lunchtime card games in 1957 at Edwards Air Force Base.
Gemini 7, Houston. We were wondering if you saw the...
Build up some 430,000 pounds of thrust. T-minus 10, 9, 8, 7, 6.
5, 4, 3, 2, 1, 0. Ignition. Engine start. We have a liftoff.
Gemini 6's actual apogee altitude is 140 nautical miles. The required apogee altitude is 146 nautical miles. To correct this condition, the command pilot will perform a height adjustment maneuver at the end of the first orbit using his aft-firing thrusters. Gemini 7 is now here in a 161 nautical mile circular orbit. Gemini 6 is now here 560 miles behind Gemini 7 in an orbit having an apogee of 146 nautical miles and a perigee of 87 nautical miles. In this present orbit, Gemini 6 would catch up with Gemini 7 in approximately 2 hours. To allow the rendezvous to occur as planned, the catch-up rate will be slowed by 2 maneuvers. The first maneuver will be at second apogee, applied in a posigrade direction to raise the perigee to 117 nautical miles. We cannot expect both spacecraft to be in exactly the same orbital plane. Therefore, at 2 hours and 42 minutes after liftoff, Gemini 6 command pilot Wallace Yaw will yaw his spacecraft to the south and execute a plane change maneuver that will place his spacecraft exactly in the same orbit with Gemini 7. Both spacecraft are now in the same orbital plane. Gemini 6, for the second time, will apply thrust at apogee to circularize his orbit at 146 nautical miles and to also slow his catch-up rate. At this point in time, Gemini 6 will be 15 miles below Gemini 7 and 140 miles behind. By this point in time, Gemini 6 should be within radar contact of Gemini 7. When the slant range distance between Gemini 6 and Gemini 7 has been reduced to approximately 32 nautical miles, Gemini 6 will initiate the first of a series of terminal phase maneuvers. These maneuvers are accomplished by the command pilot placing the nose of his spacecraft at his target, Gemini 7, and thrusting along the line of sight. There will be 2 mid-course correction maneuvers, probably here and here. These maneuvers will place him on a trajectory that will be slightly below and in front of Gemini 7. At this point, he will perform a velocity match or braking maneuver that will bring about rendezvous on us as well.
Break at 0.48 nautical miles, 660 feet.
全6号と7号の距離はですね、大体
300 feet. We're directly below them. 180 feet. 120 feet. Holding 120 feet, Wally.
何度も成功です。
Ask him what their range is now.
About 20 feet. Yeah, we're sitting up here playing bridge together. We're in formation with 7. Everything is go here.
All right. Roger, congratulations. Excellent.
Thank you. It was a lot of fun. Rendezvous and docking are most essential to complete the Apollo lunar mission. Now, on this mission with Gemini 7, we in 6 came within about a foot of Gemini 7.
The Weber ejection seat was a lightened version of the T-37 jet trainer seat. The LLRV spec required the entire seat assembly with its solid rocket motor, pilot's parachute, and rails had to be less than 100 pounds, a tough requirement. The seat system was designed with a precise CG-controlled offset from the solid rocket thrust line by a little over 2 inches, just enough to ensure that the 500 millisecond burn time would result in the seat man assembly sweeping a 45-degree angle during the powered portion of the trajectory. This design statistically assured maximum reliability for the largest range of the vehicle attitudes at ejection. The CG offset resulted in a normal profile of the seat man assembly performing a 2 1 1/2 forward tumble prior to the pyrotechnic butt snapper kicking the pilot out of the seat. The variation in the pilot's CG over time required that all pilots and astronauts flying the LLRVs and LLTVs be measured in a special CG fixture every few months in Weber's plant in Burbank, California, and their personalized seat cushions modified as needed. This ingenious system worked flawlessly 3 times out of 3 times, with no injuries. Quite an accomplishment. To maintain LLRV and LLTV CG control, we used lead shot loaded in cans bolted on the legs to account for different pilot weights. The picture on the right is a live shot of a Weber volunteer riding in the seat in a 0-0 condition from the lakeshore north of LA. Quite a demonstration for future customers. After Gemini 8 flew, its sidearm controller became a source of one of our several LLRV 3-axis sidearm controllers. After Gemini 6A's sidearm was modified and used LLRV's number 1's upgrade. Crew had landed in the middle of the Pacific Ocean as an emergency. Their spacecraft control rocket fuel was exhausted to a stuck thruster, which rotated the Gemini, docked with the Agena rocket, very high rotational speeds. The crew finally got stopped. A couple of months after the Gemini 8 mission, Neil Armstrong was visiting the Bell Aerosystem plant in Niagara Falls. Ken Levin and spouse Wilda and Sandra, my spouse, and I took Neil to dinner in the new Seagram's Tower rotating restaurant overlooking the Horseshoe Falls in Canada. Neil told us the story of the first docking, their subsequent emergency landing in the Pacific. The emergency was caused by the excessive use of fuel by the stuck rocket, the Gemini capsule. Started docked Gemini with the Agena rocket to spin. The spin continued accelerating after they separated from the Agena. And by that time, could only scan the switches and instruments in their capsule by rotating their eyeballs. Turning their heads was too painful due to the G's induced by the high spin rate. By the time they got the stuck rocket turned off, they had to abort the scheduled landing in the Atlantic, land earlier in the Pacific. The closest aircraft carrier was about 3 hours away from their landing site in 28-foot seas. When I recently checked the NASA website, the images of the sea state did not match the story. Then I realized I was the only living survivor of that dinner in 1966. As I thought about it, it dawned on me, though, that my recent emails with Dave Scott, Neil's partner in the Gemini 8 capsule, would be a great source to verify my memory of Neil's story. Dave responded and verified my memory of Neil's story in this recent email on August 10th, 2015. Wayne, you have a better memory than NASA of today, but not surprisingly. You were picked up by the destroyer USS Mason approximately 3 hours after splashdown. The problem with the sea state was the unreported 20-foot about swells. Perhaps the best source of the story can be found on NASA's website under official Gemini 8 report. Keep at it with your memoirs. You do have many good stories to tell. Best, Dave. This modified Gemini 3-axis sidearm attitude controller was used in the LLRV number 1 and another identical one in LLRV number 2, starting with the LLRV number 1 flight number 86 in March 1966. The LLRV control system components, such as resolvers and potentiometers, were used to replace the light components in the Gemini configuration. I will narrate each of these major setbacks to getting Neil trained as planned for the first launch. These setbacks caused Neil to only receive 6 LLTV flights that were made in Houston 1 month before launch on Apollo 11 on July 16, 1969. He had 21 LLRV flights from March 23, 1967 to May 8, 1968, all at Houston. During the LLRV research flying at NASA FRC, we operated under a decades-long culture of mission control, metering ground station, support to pilots flying experimental aircraft. We had alternative systems to predict fuel remaining as warning sensors, particularly for environments which are corrosive for sensors immersed in hydrogen peroxide tanks. NASA MSC crews sent for training in the latter part of the research flying at Edwards included pilots, technicians, mechanics, and 1 operations engineer. Early operations at Ellington Field at NASA MSC were supported by my Bell Aerosystems crew, which included a Bell rocket systems engineer who understood the techniques used at Edwards. Unfortunately, the MSC operations engineer serving as the mission controller for the LLRV flights ignored the inputs of my Bell rocket engineer to advise Neil to terminate his lift rocket's burn, based on the time chamber pressure telemetering data independent of the warning light. Worse yet, he never instructed Neil to close the collective stick to shut down the lift system after the hydrogen peroxide was exhausted. With the lift rocket valve open and continuing to exhaust the helium pressure gas needed to retain attitude control using the reserve attitude rocket fuel. Reserve fuel was designed in the tank feed system standpipe in each tank, ensuring retention of enough attitude fuel to make a safe landing. Cultural differences between Edwards and Houston operations was really the root cause of this accident, and I take responsibility for not recognizing this early enough to call it before the mistakes were made. The seat vent separator or pyrotechnic rotary actuator, shown here is the one actuated in Armstrong's ejection, which was caused by lift rocket fuel exhaustion and inadvertent venting of the helium pressure gas. The actuator with its harness was returned from a Bell crew chief in Houston as part of a miscellaneous collection of LLRV parts. This rotary actuator has been x-rayed in 2013, indicating no propellant remains in the actuator cartridge chamber. Notice the harness the pilot sat on is wound up into the retracted position from the ejection sequence. Neil on the chute with lots of safe recovery altitude. Probably a half hour after Neil's ejection, we held a post-flight briefing. I was sitting next to Neil, and as he continued to talk, he began lisping his speech, much to his surprise. Turned out he was just discovering he had bit his tongue during his ejection seat rocket ride. His tongue was swelling up on him, a certainly acceptable result compared to the alternatives. I always envisioned making a cartoon showing the half-burned snake that crawled out from under the wreckage that afternoon when the crane lifted the wreckage to remove it from the crash site, saying, "What the heck was that?" By removing the emergency lift rocket system, too unreliable for astronaut use, the most critical use of newly available weight savings for upgrades was the ejection seat, using only a fraction of the savings available. In early summer of 1966, Neil Armstrong and I returned to Edwards Air Force Base to witness the test firing of the upgraded ejection seat, including the new cockpit design with improved limb visibility simulation. I was standing close to Neil for the test firing, which appeared quite tenuous at the time, as the seat dummy had pitch and roll gyrations as it left the test fixture. Without waiting around, Neil jumped in his NASA's vehicle and took off, not too happy. It was declared a successful test, however, as the unusual behavior in the flight trajectory was determined to have been caused by the dummy's boot snagging the cockpit instrument panel as it left the ejection seat cockpit rail structure, thus imparting abnormal forces as the top slipper was out of the seat rail when the boot hit a clearance problem, not existence in the limb design. The next two slides are about this test. 1966, this photo was taken at Weber Aircraft in Burbank. The photo shows an ejection seat dummy lying in the desert floor after an ejection seat test, and the crew all walking away from the scene. The caption on the photo reads, "Oh well, he was just an Army pilot." I got in trouble with Jack's wife that night at a retirement party for Joe Venzel, the flight operations director for FRC. Before Jack could fly the LLRV, he needed to lose 30 pounds to meet our LLRV weight targets for takeoff. So we both went on a 10-week weight loss campaign, betting a $1 a pound on the cumulative net sum of the variances on each Monday morning weigh-ins. Loss variances were measured from the straight line loss progress over the 10 weeks. I was somewhat behind on dollars earned till we were on a trip to Bell in Niagara Falls. On that trip, we were eating out. When Jack left the table, I would have the waitress bring all the desserts to Jack, and of course, then we stayed pretty even on dollars till the end. I had a freezer and cooking capability at the LLRV South Base hangar, and my lunches were small steaks and veggies. One Saturday workday, we arrived to find our LLRV hangar had been broken into. Crew's tools were gone. They all kidded me when my reaction was visibly more upset when I discovered my luncheon steaks were also stolen. One of the Air Force guards was determined to be guilty of the thefts. Notice all personnel walking away. This flight was to be the last checkout of the LLTV before Neil Armstrong was to start training flights the next day. A small NASA flight operations team at Ellington Field had spent several months at Edwards with LLRV flight test operations as observers. However, under the very busy training operations at Ellington, it was a significantly different culture than the flight research operations at Edwards. The research culture had treated the LLRVs deserving the traditional research flight safety considerations, including the close monitoring of wind shear before flying. Operational culture in Houston, the large fleet of T-38s, a total aircraft inventory approaching 100 aircraft, allowed the LLTV to take off that Sunday with an undetected wind shear condition far exceeding the LLTV control capability. Joe Algrani, NASA's chief pilot at Ellington, owed his life to the modified ejection seat, including a new, more powerful rocket catapult, when he ejected 0.3 of a second at 120 feet per second sink rate before impact with the ground. The ejection seat performance was way outside the expectations of the ejection system capability. After this accident, NASA removed the operation engineer from his duty as the ground station flight controller, put him in charge of vehicle maintenance, and brought over 20 new mission controllers responsible for all flight operations, training every day for improving the safety of flight operations. After the loss of LLTV number 1, resulting, as it turned out, to limit Neil to only 3 days of LLTV training flights, one month before Apollo 11 launch, the LLTV number 3 was rushed to be tested in the NASA Langley Wind Tunnel, and those tests were critical in providing engineering data to revamp the operational procedures and make a few aerodynamic hardware changes to reduce flight risk. NASA employed a dedicated Air Force meteorological unit attached to the LLTV operations for the rest of the program, finally getting the message the LLTV was not just another T-38 to hop in and go fly. This dramatic photo from the 16mm film of the LLTV number 2 successful ejection by the pilot Stu Present shows the ejection rocket flaming out the jet engine. This was the only hardware failure of the 3 ejections and was caused by an undetected failure mode of the so-called product improvement by GE of the jet engine's DC generator. Stu was killed the next year in a T-38 accident. Ejection rocket blast flamed out the jet engine, spun the engine and DC generator down. Only then was the undetected high magnetic field released, which had disabled the emergency electrical bus switchover circuit, keeping the battery offline. Once the battery came online and powered the flight controls for the vehicle attitude rocket system, the LLRV's attitude system brought it in straight and level for the vertical landing. With no jet engine thrust, it crashed and was destroyed. The film footage and the telemetering data, it only took a few hours to pin down the cause of the crash. The LLRV at Edwards in a nice pitch-up attitude, causing a braking maneuver. All flights required a helicopter chase with cameramen, also a fire truck and ambulance standby. This shot shows the little used South Base runway and a B-58 and B-47 parked. This was one of the first flights before the casters were removed from the landing gear to prevent rolling after touchdown. This shot of our complex at the South Base shows the Butler building to house 2 LLRVs and the trailers for office space, plus the ramp with a mobile control van, the LLRV, and fire truck. We modified the cockpit enclosure to simulate a limb window. NASA MSC also requested the addition of an anemometer to sense wind speed and direction. During our presentation in Houston on the Bell costs for these changes for the LLTVs, as the Bell technical director for the LLTVs, I remember Joe Algrani NASA's chief pilot in MSC, equating the cost as to how many Cadillacs you could buy for those dollars. A weird negotiating tactic. This shows the modified cockpit with the instrument panel moved from the center to the right side. The rear platform housed the avionics package and the drogue chute for stabilization if the emergency lift rockets were used. It was removed with the emergency lift rockets before going to Houston. A good color shot of the desert before the cockpit mods. Joe Walker in the early cockpit. Don Malik, the second LLRV pilot, the only surviving LLRV pilot from Edwards. Colonel Jack Kluber, U.S. Army, the third LLRV pilot. The XB-70's Mach 3 experimental aircraft flight schedule overlapped with our LLRV flight schedule quite often. System's reliability on the experimental aircraft frequently resulted in emergency landings which required all available fire trucks be on standby next to the runway. This meant our LLRV fueling operations had to be delayed till we got our fire truck back. On one such occasion, we had just gotten our fire truck back when one of our LLRV technicians asked a new crew member he was teaching to drive to take him back to the hangar to get something. 2 or 3 test pilots stepped away from the back of the NASA station wagon when they both got in, but the new engineer mistakenly dropped it into reverse and nervously stepped on the gas, shooting the station wagon back into the fire truck's foam tank, with foam spilling all over the concrete. Right away, the radio call to the control tower reporting they had just been hit by a NASA station wagon and needed a replacement fire truck for our flight operations started a real fuss. A couple of days later, after much ado, I was in the famous Bickle barrel for my first and last time. Bill Bickle, our center director, had won me back to zero from the good standing I had earned so far. Thanks to our center's security officer, a former Air Force officer, none of us went to jail or were fined. On June 10th, 1966, I was checking into Bell as technical director on the LLTV and received a call from NASA about the terrible accident. I'm on the right. Notice the rack on the van. We were told I could not get a pickup to get fast access to the cockpit, so I put a rack on the van. As soon as we bent the springs by overloading it and putting it back on blocks, we removed the rack. On this crew shot, I'm second from right. This NASA control van was moved from the White Sands, New Mexico operation to Ellington Field for the LLTV operations after the LLTV number 1 crash. I left NASA and joined Bell as the LLTV technical director. NASA MSC contracts managers were quite upset with the significant increase in the Bell LLTV contract bid over and above what they had planned. They held a meeting at NASA headquarters to have me barred from participating in the LLTV program at Bell. Lloyd Walsh, the NASA FRC contracts manager, was in the meeting and essentially said could not meet their tight schedule requirements reliably without my expertise. MSC's fallback was to bar me from the Bell negotiations. Thus I became known as Mr. X, as I was across the street in a hotel conference room with cabinets for drawings and documents, able to advise the Bell negotiating team and giving inputs during their frequent ability to caucus privately and have me on the telephone. John Matson, the Weber Corporation ejection seat manager in Burbank, hosted both NASA and Bell invitees to the first Super Bowl, January 15th, 1967. Joel Grani, chief pilot for NASA MSC, and his deputy Bud Ream flew their T-38s to Burbank. I came from Buffalo via a weekend stopover in Phoenix to visit my parents. LAX airport was fogged in that Sunday morning, and by the time it opened up for my flight from Phoenix to land, it was almost halftime when I arrived at the Coliseum in Los Angeles. The ticket booth manager, understanding why I missed the Weber group, took me in to the 50-yard line, about the third row. I sat down and the first half ended. Halftime started with two rocket belts flying from opposing goal lines, one of the operators living in the same block of our house in Buffalo. I was shocked this halftime performance had been a secret. After the LLTV number 1 crash, the LLTV flight operations grew from the 4 or 5 engineers managing the vehicle maintenance, pre-flight servicing, and ground and flight operations to about 25 personnel from mission control to handle all the flight operations and practice daily flight simulations. These actions came a bit late in the program, but certainly provided the attention that the flight safety dictated. The aerial view of the LLTV facilities at the end of the runways at Ellington Field, Houston. This is the LLTV number 3 being tested for drag characteristics in the NASA Langley Research Center full-scale wind tunnel. This NASA LLRV poster was signed by the LLRV pilots Don Malik and Jack Kluver. Neil also signed it as having flown the LLRV, the LLTV, and the LIM. The only other astronaut to have the same experience was Pete Conrad, Apollo 12 commander. The LLRV's legacy in leading the way for the LLTV and LIM designs, all leading to 6 successful lunar landings, is remarkable, considering it was the first all fly-by-wire VTOL, and at that, using analog electronics. In less than a decade, this project, in spite of funding squabbles, opposition from automatic landing system proponents, accidents, and development challenges, got the job done, and in no small part was responsible for the 6 successful Apollo landings. The Aviation Week cover for June 30th, 1969 featured a picture of one of Neil's LLTV training flights made June 14th through the 16th, before his Apollo 11 launch, July 16th, 1969. The aluminum structure shown is a typical LLRV or LLTV leg assembly designed with the hydraulic struts for the landing gear to carry landing loads and represented decades of Bell Aerosystems structural design expertise. Their LLRV design provided ample safety margins, as minor flaws identified by conventional X-ray quality control inspections were controversial. Bell had 3 LLTVs on their shipping dock, ready for delivery to NASA in Houston in August and September of 1967. The then recent Apollo disaster, in which the 3 astronauts were fatally trapped in the capsule fire during a checkout, resulted in NASA's quality control exercising veto power via differences in weld inspection specifications over the Bell engineering traditions. A 2-month delay was experienced in the already late training operations. The problem was only solved by subjecting identically processed joints as shown to fatigue tests many times the design requirements, which passed with flying colors. As the Bell LTV technical director, this was my most formidable management and legal challenge to deliver LLTVs for Deke Slayton and the astronauts. This LLTV number 3 is hanging in the NASA JSC Teague Auditorium in Houston, and someday, hopefully, will be in the Smithsonian Aerospace Museum in Washington, D.C. In the year 2000, I received a grant from NASA to produce the monograph shown here. My co-authors were Gene Matranga, the initial assistant program manager for NASA FRC, later taking over as project manager's position, and Cal Jarvis, our controls engineer. We took a couple of years to write it, and it was published in 2004. This is page 1 of the foreword Neil wrote for the monograph. The next 3 slides continue the foreword. Page 1A of foreword. Page 1B of foreword. Page 2 of foreword. This letter of commendation from the director of the NASA Manned Spacecraft Center, now the Johnson Spacecraft Center, or JSC, Robert Gilruth, named test pilots Joe Walker, Don Malik, Colonel Jack Kluver, and Don Bellman, our first LLRB project manager, Gene Matranga, and C.W. Ottinger. In 2000, the Joe Walker Intermediate School in Lancaster, California, approached me to work with their science class to replace the stolen model of the LLRV that Joe's widow had donated to the school. I recruited 2 LLRV crew chiefs and a rocket shop technician to assist me in tutoring the 7 teams of students to build a suitable replacement. This year's project culminated in them earning my donated tile mural for their library, 5 foot by 9 foot, depicting their activity. They earned the mural by creating the slogan, "Learn math and science, one small step for schools across the nation, one giant leap for our future." All 60 students were given poster-size canvas copies of the mural with a certificate that Neil and I created. Joe Walker was Neil's boss before he became an astronaut, and both were featured in the mural. Neil suggested I get a retired teacher to help me with my writing skills for this certificate. I had to tell him I was married to one. In September 2014, I proposed to NASA that we have a 50th anniversary panel for the first flight of the LLRV, which was on October 30th, 1964. We were able to have that panel on October 29th, 2014. A full video is 1 hour and 48 minutes. The panel was as shown above. I was the youngest at 81, and Dave Stoddard the oldest at 90. I have a 38-minute version of the video, and both are on ElectroSTEM's YouTube channel. This Air Force clip includes the LLRV. In the spring of 1962, I was given the choice of taking the NASA Flight Test Project Engineer position for either the Air Force X-20A Dinosaur project or the Lunar Landing Research Vehicle, or LLRV. I was already working as the NASA plant rep for the LLRV at the Bell Aerosystems plant in Niagara Falls, New York in 1963. When the Dinosaur was canceled, I had made the right choice. In 1957, as a GE 79 engine engineering rep on the F-104 flight test program, I was in the Edwards Air Force Base Fighter Ops Ready Room playing ping pong with another rep as my partner, and the two opponents were Captain James Wood, later to become the Chief Air Force Dinosaur pilot, and Captain Gordon Cooper, later selected as a Mercury astronaut. They were waiting for their F-104 test flights, but in the middle of the game, the control tower radioed for them to take a T-bird and join up with a crippled Boeing KC-135 or 707 fuel tanker orbiting around Rogers Dry Lake Bed. The KC-135 had been hit underneath by a test pilot school's T-bird taking off, which crashed, and the test pilot killed, leaving the KC-135 with no hydraulics, electrical power, or communication. Eventually, the KC-135 made a gear-up emergency landing on the lake bed and was rebuilt for flight status at Edwards. In the 1990s, I was talking with Stan Butchart, the NASA pilot on board as co-pilot for the KC-135, which gave me the first-hand story as to how they communicated with Woods and Cooper in the T-bird that day in 1957. Handwritten notes on notepads were held up both canopies to give the KC-135's visual inspection results as the T-bird flew around the KC-135 to let them know via reading notepads in close formation. Also in 1980, at an SETP annual symposium, my wife and I were with Colonel James Woods, who told us he had retired from the Air Force and served as the Shah of Iran's personal pilot and brought him out of Iran in his Boeing 707 when the revolution drove him out. About 5 months into the LLRV design at Bell, a solution was found to several challenges, namely tip-over risk on landings, weight limitations driven by jet engine availability, center of gravity problems, and jet engine inlet distortion. Move the Dern cockpit out front and mitigate all the above concerns. As it turned out, the LLRV LLTV project was an aviation first, the first VTOL to be controlled in all three axes with fly-by-wire flight controls, and furthermore with analog electronics. The real genius of the LLRV LLTV design is credited to Walt Rusnak, the Bell engineer who conceived the unique but efficient method of utilizing the gimbal jet engine to provide the gravity offset for the 5/6 Earth G cancellation, as well as the vertical and horizontal aerodynamic drag forces. Also, the reaction control system for the vehicle attitude control through the hydrogen peroxide attitude rockets handled that aerodynamic force cancellation, resulting in meeting the goal of performing earthbound free flight simulation of the lunar flying conditions in a 1/6 G and vacuum environment over a half century ago. The Apollo astronauts are quite satisfied with the extent of the free flight trajectory available for the LLRV and LLTV for the purpose of training. Typically, they practice making changes to their landing target and that final landing approach to be familiar with the time to maneuver with rapidly diminishing fuel reserves. Jack was the Army program manager in the Pentagon in 1967 for the Lockheed Cheyenne helicopter program. He requested the Army allow him to fly the LLRV in 1967 at Ellington Field for a demo flight for the astronauts. He was busy in Niagara Falls by then with the LLTVs. I understand he put on a great flight demo. In April 2011, I delivered a tribute to Jack at his memorial. One of the last LLRV flights at Edwards, Jack decided to see how high he could take the LLRV as he had a full load of fuel, as was the standard practice, and his primary mission for that flight was compatible. No record was ever made of the altitude he reached, but on our 1999 35th anniversary celebration of the first flight at the SETP headquarters in Lancaster, he and the LLRV project manager, Gene Matranga, talked about that flight. I was working for Bell by then. Jack said he knows it was over 5,000 feet. Couldn't remember how much over. Gene thought it was much higher, so a good task would be to calculate what was possible. Presented some analysis to Don Malik later, and our conclusion was around 7,000 feet was the best guess. A good summary to be proud of. This summary of training effectiveness is from an unpublished NASA document I co-authored with John Kelly titled A Toolset for an Advanced Landing Technology Development and Training Program. John wrote this paragraph on training effectiveness metric. There is an aspect of training that goes beyond fidelity. One can have all of the cues right, all of the visuals right, etc., but still miss something critical to the effectiveness of the training. Gene Cernan summarizes succinctly, you have to eject or land. Those are the only two options. Think of it with this analogy. The ultimate training to learn how to fly an aircraft is to go fly the aircraft. For a moonlander or other destination beyond LEO or low Earth orbit, there is no such analog. You work with the next closest thing you can in an Earth analog, an Earth lander. But just as in the airplane, you have to make the landing. Something beyond the fundamentals of the physics need to be put into the psychology of the task. I must make this landing. I can't rely on anyone else. If I don't make this landing, really bad things are going to happen. So in this case, the fidelity of the physics is not nearly as important as the fidelity of the psychology. So physical effectiveness is important, but psychological effectiveness is also very important and must be taken into account. That is why this metric is here. There is something in the concept, training with real consequences, that is meant to be captured here. On December 9th, 2008, the 4 Apollo astronauts, Neil Armstrong, Apollo 11 commander on the left, Gene Cernan, Apollo 17 commander on the right, Harrison Jack Schmitt, Apollo 17 limb pilot, background, and John Young, Apollo 16 commander, not shown, and myself, center, briefed the NASA Constellation Altair Lunar Lander Project Office on the LLRV and LLTV programs. Our recommendations were to provide the Constellation program with a free flight LLTV design and built with the new technologies available today, a half century since the Apollo program. On March 6, 2016, Gene Cernan was present in Boulder, Colorado for the last day of the Boulder International 2016 Film Festival, where his new film, Last Man on the Moon, was presented. After the showing of the film and a 30-minute Q&A, I was able to meet with him briefly after the media interviews. The last I had been with him was at the 2012 Space Festival in Tucson, Arizona.